So thank you, Danny. Does this thing work? Can you all hear me? All right, bueno. So the title here is a bit tongue-in-cheek, of course. It's designed to get attention. But there is a grain of truth to it. There is a gold rush on. And we here in Texas, of course, are no strangers to gold rush. Some of you will recognize this. That is Spindletop, January 10th, 1901. And it kicked off the oil boom in Texas. The Lucas #1 well. Within 2 years, so October 6, 1902, one well was replaced by a forest of them, right? Fortunes were made. And today, the oil market, annual oil market is $2.1 trillion. It is worth more than the top 10 metal markets combined. Not just more than twice as much as the top 10 metal markets combined. Right? It is also cheap, abundant hydrocarbons have transformed civilization. Right? They are heat, they're light, they're mobility. They have lifted billions from poverty without exaggeration, and they have fueled the information age. Right? We owe our civilization as it is today to hydrocarbons. But there is a downside, right? Hydrocarbons come with emissions, and our new challenge is getting to net zero. So hydrocarbon or human emissions today total about 35 billion tons per year. 35 gigatons of CO2 per year. So the graph you see there is billions of tons of emissions on the vertical and time on the horizontal. It starts in 2000. Where the black line ends is the record. Right? That's historic emissions up to 2019. Getting to net zero is a series of wedges, and it is an all hands on deck sort of a problem. Right? It requires all solutions. So everybody has their own pet mix of solutions, but everyone who thinks about it seriously comes up with something fairly similar. It's about a third renewables, so wind, solar, perhaps hydro. It's about a third efficiency gains, and it's about a third everything else. Right? Nuclear, fuel switching, CCS, carbon capture and storage, which of course is the topic of our talk today. So for those unfamiliar, carbon capture and storage is the idea of taking emissions from a point source, power plant, cement plant, whatever, an industrial facility. Could be direct air capture, but it's an industrial facility, it's a point. Capture the CO2, filter it, purify it, compress it, transport it to a storage site, and inject it deep underground. Same kind of reservoirs that we get oil and gas out of. So in some ways, this is just putting the carbon back where it came from. Right? And you might look at that graph and think, that little red wedge for CCS, that was 9%. Surely that's kind of in the noise. Why are we bothering with this? And it's a fair question. We bother with it because this is a uniquely flexible solution that can be applied to all kinds of different emission sources. So we can use it on existing infrastructure right now without having to wait for infrastructure to serve out its life or replace it at high cost right now. We can also use it on hard to abate industries. So things like steel, cement, petrochemicals, hydrogen production, they all emit CO2 as part of the process. Right? It's not just the energy consumption. You can substitute renewables and you're still left with the process emissions. It's the calcium carbonate breakdown in cement. It's the coking in steel. It's the steam reforming of natural gas to make hydrogen. All of those things, no matter where you get the energy, they emit large amounts of CO2. Cement alone accounts for about 8% of global emissions. CCS is how you deal with that. It also allows you to keep dispatchable power in the mix. So, as you may have noticed, the sun does not shine all the time. Wind does not blow all the time. Night is a thing, right? But we still need power at night. Dispatchable power, as it's called, on-demand combustion power, is a necessity. And you either massively overbuild renewable capacity to keep enough capacity in the system when wind and sunlight are low, or you build huge batteries, or You keep some combustion power and you abate the emissions. CCS. 2 more bullets. One is negative emissions. Increasingly, filtering CO2 out of ambient air is part of the solution. Right? We need to claw some of this back. Fine, we can do that. But once you claw it back, what do you do with it? CCS, you inject it. And the last 2 are about strategic risk management. IPCC did a study looking at different pathways to net zero. And what if you take out solar and wind? Or what if you say no nuclear? What if you take out CCS? Most of these things are plus and minus, right? They make a few % difference in the cost. They sort of take some pathways out of off the table. The only one that made a big difference was taking out CCS. That one more than doubled the cost, and it drastically limited the paths to net zero. Basically, it relies on large-scale behavior change and massive reforestation. Maybe we'll get there. Maybe that works, but having CCS in the portfolio is strategic risk management. We've actually been doing it for about 50 years. Believe it or not, the first CO2 injection occurred in West Texas, 1972, for enhanced oil recovery. Right? There are about 67 projects on this map, I think, all over the world, as you can see. Many of them pilots, some commercial scale. Most of those commercial scale, of course, are CO2 EOR, or enhanced oil recovery projects, because that's what's paid. There's a handful that are about dedicated CO2 storage. And some people look at that and they say, this technology doesn't work. Not true. Technology works. What hasn't worked are the incentives. So over time, Poland and Finland were the first 2 countries with a carbon price, 1990. And it was a pathetic price. It was about $1 a ton, if I remember right, $3 a ton, something like that. The sort of thing that you just pay and you keep emitting. But that's price, it's number of, or % of the world's emissions on the vertical and time on the horizontal. And the different colors represent different countries. The takeaway message with this is, for a long time, very few countries put any price on carbon emissions. That is now changing. And I'll give you a sense of how rapidly it's changing. You don't have to read the details in this, but these are global carbon prices as of 2020. Right? So you can see there's a number of countries. Those are the things on the vertical. Most are offering something on the order of maybe $20 a ton, $15 a ton, something like that. A few get over 50, one gets over 100. 2023, and I'll go back and forth. Look at the difference in 3 years. The US is not one of those countries. We do not have a carbon price. What we have instead is a tax credit for storing carbon. 5 years ago, when I joined the Bureau, that credit was $10 a ton. And again, it incentivized absolutely nothing. The tax reforms under Trump changed that to $50 a ton. That was enough to get people's attention. So $50 a ton for carbon from anthropogenic sources stored geologically. The Inflation Reduction Act changed $50 to $85. $180 if you get your carbon from air, from ambient air. That gets attention. Just this week, JP Morgan Chase came out with their climate report with a message from our chairman and CEO, Jamie Dimon. You can't read it, so I'll enlarge it. The key bits in this: energy transition, right? We believe that a successful transition generates economic growth, preserves energy security and affordability, mitigates the worst impacts of climate change. In order to successfully achieve that transition, a massive ramp up to the tune of $4 trillion of annual investment will be needed, bringing with it the potential to generate a wave of growth and opportunity that hasn't been seen since the first industrial revolution. There is a new gold rush on, make no mistake. $4 trillion. So just in the last 3 months, September, Equinor farms into a storage project on the Gulf Coast. September 28th, Trace Carbon Solutions announces Evergreen Sequestration Hub in Louisiana. This is a sequestration hub for carbon emissions. Bring me your emissions, we'll sequester them. November 7th, 3 weeks ago, BlackRock invests $550 million in Oxy's direct air capture facility. Last week, Air Products goes ahead with $7 billion hydrogen project with CCS to abate the emissions. Nor is this just US. Dow, $6.5 billion investment in a zero emissions cracker in Alberta, Canada. This morning, ADNOC, the UAE state oil company, made the final investment decision on a $17 billion hydrogen project with CCS. Right? There is serious money here. Close to home, on the Gulf Coast, over the last 2 years, we now have 49, as best I can count them, 49 announced storage projects, publicly announced projects with leases, some with permit applications filed, some drilling wells. There's money going into these things. It's not simply press announcement. So the dots that you see on the map, the blue dots, are announced projects, and the size of the bubble corresponds to the announced capacity. So the dark blue ones have actually announced capacity. We have a storage site with X megatons. And to give you some idea, the smallest of those blue dots are on the order of 10 to 20 million tons total capacity. And I'm not sure that there are any of them at that scale. The biggest ones are 500 million tons of capacity up to a gigaton of capacity. Claimed, right? This is announcement, it's a press release, it's designed to generate enthusiasm, so take it with a pinch of salt. But nevertheless, 500 million to 1 billion tons of carbon. The light blue ones have not announced a capacity. They've announced a rate. And I've multiplied it by 20 years to infer a capacity, because most of these projects go 20 to 30 years. And again, you see, same scale, they're up to about a gigaton of storage. The white ones have not announced rate or total capacity, so who knows? But if you add these things up, the ones with announced capacity are over 7 billion tons of storage, 7 gigatons. The background on this, the gray dots, are emissions. So the biggest of those sources is about 10 megatons a year, they're power plants. And they get down to a few hundred thousand tons, or a few tens of thousands of tons per year. The ones you see offshore, those are platforms. It's the compression on the platforms emitting 20,000, 100,000 tons a year. It's not insignificant. But if you were to take all of the emissions, Texas, by the way, leads the US in point source CO2 emissions, about 350 million tons per year. Louisiana is number 2, with about 150 million tons per year. So 500 million tons in round numbers between the two of them. If you multiply that by 20 years, 500 million times 20 years, 10 gigatons, right? We've got, theoretically, enough storage already announced to store 15, 20 years worth of Louisiana and Texas emissions. Gulf of Mexico is what's known as a super basin in petroleum. It is one of those top 10 performers in the world. Right? West Siberia, Arabian Basin, Gulf of Mexico. They're in the same class. The strat column here from Galloway shows you from Jurassic up to Pleistocene the various reservoirs. Every one of those red dots denotes a proven producing petroleum reservoir. We have proven production from Jurassic to Pleistocene at every stratigraphic interval, right? Seems like a great place for CCS, right? Reservoirs, traps, seals, volumetrics, right? We know this stuff from oil and gas. We know how buoyant fluids work in the subsurface. How different can it be, right? In oil and gas, we calculate volumetrics by pore space and saturation. So you take a bulk rock volume within a tract, within a closure, multiply it by net to gross, multiply it by porosity fraction, times 1 minus irreducible water saturation, and you have oil in place. Multiply that by a recovery factor, and you have a pretty good idea of what you can get out. Do the same for CO2, right? Buoyant fluid, reservoir, seals, subsurface, how different can it be? Bulk rock volume, net to gross times porosity, that gets you pore volume. We talk about CO2 in mass rather than volume, so we multiply it by a density. And a storage efficiency, a fraction of the pore space that we think we ought to be able to occupy. Right? And that's a slippery number, but people tend to use something on the order of 2, 3, 4%, maybe 10%, and you'll see outliers in both directions. But some fraction of the pore space that we think we can occupy with CO2. Right? How difficult can it be? Some of my colleagues, before I arrived, did this analysis for the Texas Gulf Coast, the Miocene storage interval on the Gulf Coast. And this is the map of capacity with 4.5% pore occupancy, or storage efficiency as it's called. For the Miocene of the Texas coast, they come up with 125 gigatons of storage. If you just look at state waters, it's 30 gigatons, but large capacities. And I have to say, it's important work. These analyses were instrumental in convincing policymakers that CCS could play a major role in climate change mitigation. However, CCS is not hydrocarbon production. And I'll highlight 3 major differences. First one is that it's a low margin gain, right? This is pollution control. Nobody wants to pay too much for pollution control. You want to pay the minimum to get the job done. The graph on the left is about cost of capture. So there's cost on the vertical and there's different sources on the horizontal. But over on the left, if you take the absolutely pure CO2 emissions from acid gas removal units in LNG, your cost of capture is $20 to $30 a ton. That's as good as it gets. You still remember the reward is about $85 a ton. So that gives you a healthy margin. But if you're looking at, say, power, coal-fired power plant, which is one of those bars in the middle, now you're talking $40 to $70 a ton. That leaves you $15 a ton to transport, store, and profit. If you're looking at direct air capture, the cost is $250 to $650 a ton on this graph. And this is literally last week's graph from IEA. That's cost of capture. You also have to transport it. Pipelines, in round numbers, $1 to $3 million a mile, maybe a bit more if you're sizing them large. This gets expensive quickly. This is a cost-constrained business. Second difference. Our goal is sequestration, not production. Right? So this is a fairly typical Gulf of Mexico setup. We've got a salt diap here in pink. We've got a bunch of reservoirs in yellow that turn up on the flanks, create a nice buoyant trap over the top. Right? Every one of these salt diapirs, almost without exception in the Gulf of Mexico, produces oil and gas from exactly this setup. And we could reuse those same reservoirs for CO2. But our goal is sequestration, not production. We don't need concentrated mobile fluids. So what we'd really rather do is inject not on the crest of this, but down on the flank, down in the syncline, where the reservoirs are probably thicker, cleaner, and less complicated. And let the CO2 migrate up dip and actually play for migration loss. Right? So take advantage of pore throat trapping. Take advantage of dissolution. Take advantage of whatever little buoyant traps we can encounter. Whether they're little fault blocks or roughness on the top of a flow unit, whatever. It all adds up. If I can get CO2 to migrate into a waste zone, as we call it in petroleum, something we can't recover from, that is super secure storage. That's not waste. That's bonus. I don't have to worry about that going anywhere. Right? One man's migration loss is another man's secure storage. Third difference is pressure buildup. We are injecting CO2 into reservoirs that are already full. And we think about buoyant fluids like oil and gas accumulating in reservoirs on geologic time, building column from the top of a trap downward. If you give it enough time, that works. You can displace the water at pressure equilibrium, everything is fine. That's not the case with CO2. We are putting it in at industrial rates, not geologic time. It is like putting it into a bowl with a fire hose, right? Sweep efficiency is all over the place. It follows the high perm streaks. Displacing the water is slow. Depends on the permeability architecture. So with this, we have limited ways of making space for the CO2 that's going into the reservoir. We can inflate the reservoir, actually raise the land surface, and it does happen. In some cases, we can track it, but it's small. It's on the order of millimeters to centimeters. You don't get much capacity that way. We can dissolve it, and again, CO2 is soluble in water. As it contacts unsaturated pore water, you will dissolve some, but that's a fairly small fraction. You don't get much space that way. We can displace the water, and we do. We push it away from the well, but the water has to go somewhere. It pushes into other water. Mostly, our space comes from compression. Right? It's compression of pre-existing brines and rock, neither of which is very compressible. Right? Pressure buildup is inevitable, and it is the key limit on CO2 storage. It's not saturation, and I'll show you an example here in a second. So, what limits pressure? We've got a graph here, pressure, depth on the vertical and pressure on the horizontal. The blue line on the left is the weight of a water column. It's hydrostatic pressure. That's what we start with. The next little blue line is the pressure limit if you've got open well bores and you're worried about lifting injection zone brines up through an open well bore. Hopefully we don't have any open well bores because that's not much of a limit. We don't have much room to build pressure between our starting point and that limit. The red line is minimum horizontal tectonic stress in a place like the Gulf of Mexico. That's your limit if you're worried about fault slip. The third line, the yellow one, is frac pressure in the sands. Our statutory limit for injection pressure is based on sand frac pressure. The gray line there is shale frac pressure, which is the limit in some countries, not the US. And the black line is lithostatic pressure. It's the weight of a column of rock. So if you look at this in terms of pressure buildup, if you start from hydrostatic, obviously it's depth dependent, but you don't have much room to build before you hit that first line. You get a little bit more if you're worried if fault slip is your limit, and you get a significant amount if you're limited by statute, if you're limited to 90% of frac pressure in the reservoir. But there are pressure limits. And I'll give you an example. This is Snøhvit, which is a Norwegian injection project in the Barents Sea. They're producing gas from one fault block, separating the CO2, and re-injecting the CO2 in the neighboring fault block. So injection is in the red circle there. It's a fluvial reservoir, variable poroperm, which is what the chart is telling you. But you can see it on seismic as well. Right? There's a modeled pattern to the amplitudes. It's heterogeneous, and no one will defend that interpretation too hard. But the view was that it would accept CO2. It would be fine. Here's the record of pressure versus time when they started injecting. Bottom hole pressure is the black line at the top, and you can see it going up and down. The red line that's hard to see is injection rate. And the take home here is that they kept having to shut the well in to let the pressure dissipate. Every time they started injecting, pressure built up. And they finally got tired of it. They kept approaching the limit, having to shut the well in. They just recompleted the well in another reservoir, which is why it suddenly goes down and stays down. But here are two 4D seismic volumes. So they're difference volumes. Seismic shot after injection minus the seismic shot before injection. And they're processed to show pressure buildup on the left and CO2 saturation on the right. So with the pressure volume, you can clearly see giant amplitude bloom around the injection well. Bounded by faults, north and south, and probably by fluvial heterogeneities, east and west. The saturation volume, there's a little bit of red bloom around the well, but I cannot tell the difference between that and the background noise. Right? You find the same little red speckles all across that image. pressure buildup is your limit, not saturation. So you come back to this, and projects that have been put together, assessed, using oil and gas volumetrics for the most part, and you go, ooh, hang on. What is realistically achievable here? Most of these projects are modeling injection with open boundaries. The idea that they can displace water effectively, mathematically, forever. Right? But what do we know about the Gulf of Mexico, and particularly the coastal reservoirs? They are heterogeneous, fluvial, deltaic reservoirs. There's a lot of stratigraphic edges to them. There are a lot of faults. There are a lot of potential geologic barriers, boundaries. This idea of open boundaries may have some trouble. The other thing, of course, is that many of these projects have neighbors. Right? They're cheek to jowl with the next project, and pressures will create effective barriers for each other. So, think we've really got open boundaries? There's two ways to look at this, and one is simply to ask the question that I do as an explorer. What if we pressured it all up? How much would you get? What's the upper limit on how much we might store here? And clearly, pressuring the entire Miocene to 90% of frac, the statutory limit, probably unrealistic. But as an exercise, what if we did? How much would you get? And my analogy for this is a gas storage tank. Right? Capacity depends on volume of the tank, of course, but it also depends on pressure rating. You don't know capacity without both of those numbers. Subsurface, not very different. So if we look at this in 1D, depth on the vertical, and various quantities on the horizontal, this is our volume. It's porosity. And this is just a compaction function, but it starts at 44% porosity at the surface, and by 4,500 meters, you're down to 10% porosity. Our allowable pressure change, I showed you pressure buildup. If we start from hydrostatic, we can calculate frac pressure. Orange curve is 80% of frac pressure. Blue curve is 90%, our statutory limit. And for the sake of argument, what if you got to 100%? This isn't gas storage. We've got a tank that's already full of brine, so we worry about compressibility. Total compressibility is not much. That's on the order of 10 to the minus fifth per megapascal. But you can see it varies with depth. The final curve in this is CO2 density. So density on the horizontal, and you see the sharp transition where you go from low density gas to supercritical fluid. Different curves, of course, reflect the effect of pressure. Higher pressure, higher density. Multiply those together, and you get a capacity. If you get to 80% of frac, you get the orange. If you get to 90%, you get the blue line. And that's 1, 2, or 3 kilograms of CO2 per cubic meter of reservoir. In terms of pore occupancy, it's not much. Right? That's on the order of 1, maybe less, 1%, maybe less. Water and rock are not very compressible. But the key here is that capacity is both depth dependent and basically a linear function of depth, which means that we can take this logic and apply it to a grid fairly easily. So if we take the original grids from that static capacity analysis of the Texas coast, and Dave Carr was very generous, he just gave me the grids. There's the map of porosity, average porosity for the Miocene storage interval, allowable pressure change, total compressibility, final CO2 density, and net reservoir thickness. Multiply it all together, and you get about 10 gigatons of capacity, which is still a lot of storage, but it's a tenth, in fact, less than a tenth of what was calculated based on 4.5% storage pore occupancy. The average pore occupancy here, storage efficiency, is about 0.5%. That's the compressibility of water and rock. And you go, oh, hang on. You just reduced my capacity by 90%. Is it really that bad? Come on, hang on. Where's the uncertainty in this, right? We can look at the uncertainty. So there's a little black star offshore Houston on both of those maps. We'll use that as a reference point. And it's a place where you have, what, on the order of 400 kilotons, 400,000 tons per square kilometer. If I look at the map, we can define some plus and minus. We can take the extremes of porosity from the map. We can take the extremes of net reservoir from the map. We can ask what would happen if you allowed pressure to dissipate into the non-net reservoir, the fine-grained sediments. We can imagine that maybe not all of the sands are completely injectable. We can play with pressure limits. If we take 80% as the likely average pressure across the storage area, maybe you get to 90%. There's an upside. Maybe you're limited by open well bores. There's a downside. So I won't go through every one of these things, but you get the idea. We can play plus and minus. And if you do, there's two tornado plots. One is in absolute numbers, and the other is in percent. Our reference capacity at that point, assuming you pressure it up to 80% of frac, is 218,000 tons per square kilometer. And you can see, if you change the pressure limit, you get a big swing. Right? We could go down by, 175,000 tons? You could end up with 5,000 tons per square kilometer. On the other hand, if you can get it up to 90% of frac, you'd add almost 200,000 tons. You'd almost double it. There's basically two categories of variables in this. One are variables that affect your pressure headroom. So pressure limit, salinity, geothermal gradient, and injection zone depth. The other categories affect your pore volume. So porosity, net to gross, net reservoir thickness. Right? It's those two variables, volume and pressure rating. The other way to look at sensitivity is just to run a Monte Carlo analysis. You put the same variables into Monte Carlo, you randomly sample from those ranges, and you calculate capacity. Over 10,000 runs of random sampling, you get a feel for the distribution. And in this case, P50 is about 212,000 tons per square kilometer. At best, P90, you get up to not quite 400,000 tons per square kilometer. There's not a lot of wiggle room in this. But there are two wild cards. One is dissolution. Right? Dissolved CO2 takes almost no space. It does not add to the pressure. And dissolution is basically an instantaneous process. Contact CO2 with unsaturated pore water to dissolve some. However, CO2 is not all that soluble in brines at reservoir conditions. So solubility ranges from about 3 to 5% at typical reservoir conditions, meaning that if you have 100 kilograms of water, it can hold 3 to 5% of its weight in CO2, 3 to 5 kilograms of CO2. So you start wondering how much water you could contact as you inject CO2. And we can play games with this. We can bracket ranges. But the models here show you a couple of scenarios. One is injection into the top of a structure. And these are 60 megatons injected 100 years post-injection. Hotter the colors, the more concentrated the CO2 is. So if you inject it into a trap, you keep it pretty concentrated. And refresh of the water and dissolution relies on convection. It'll happen, but it's slow. It's geologic time. On the other hand, if we can get CO2 to migrate, we're bringing the CO2 to the water instead of the other way around. We can do a little better. And you might, at best, contact maybe 10% of the pore space that you pressure up. So that could add 10% at 0.5% or 5% solubility adds 0.5% to our storage efficiency. You might get to 1% at best. The other wild card, which is a whole lot more impactful, is fluid production. All right, this is a North Sea platform that actually did CCS. It's a gas field, high CO2 gas field. They separated the CO2 and re-injected it. But the curve there shows you field pressure over time. And you can see the decline from 400 something bars down to 50 bars at abandonment. If you can balance CO2 injection with withdrawal of some other fluid, hydrocarbon or usually water, you can manage pressure. The trick, of course, is you got to do something with the water. Saline, nasty brines, they may have hydrocarbons, they may have heavy metals. This is not easy. If you have to re-inject it, you're just putting the problem somewhere else. The only way you really get out of jail for free is if you can overboard the water, which is routinely done in hydrocarbon production. If it's environmentally acceptable, and the rules have yet to be written for CCS on this, but if it's environmentally acceptable, there is a huge pressure management mechanism offshore. Onshore, we're kind of stuck with it. So hard to exceed 1% average storage efficiency without water production. This is a catalog published by the Oil and Gas Climate Initiative of all of the projects that they can see worldwide that have published numbers. So this is the storage efficiencies that, from 224 projects that they are basing their models on. Right? It ranges from less than 1% up to 25%. And these guys may get 25% poor occupancy. I don't know. What I can tell you is that they get it only one of two ways. Either they produce water, fine, manage pressure, or they define their project boundaries such that CO2 fills those, but the pressure goes into the neighbor's space and probably the neighbors of neighbors. Right? Their pressure impact goes way beyond their lease boundaries. And this brings me to the second way you can look at this. It's called area of review, and it's a legal construct by the EPA for injection wells. So the idea here is you've got an injection well on the left. Right? It's injecting CO2 into a reservoir at depth, and the CO2 plume spreads out a little bit from the well. That's the blue bit. But the pressure, the shaded region in the reservoir, goes a whole lot farther. And it tapers off with distance. But there's a protected aquifer that you worry about. Our statutory requirement from EPA is to protect fresh water. That's the thing they worry about. So that's the blue bit at the top. Now, next to the well, you pressure up the reservoir. If there were an open wellbore, you'd raise brines way above surface, right? Because we've pressured the reservoir. It's called hydraulic head, and that's represented by the red line at the top. So next to the well, high pressure, hydraulic head will lift injection zone brines way above surface. You get a fountain. With distance, of course, that tapers off. And you see the point at which the red line dips below the base of fresh water, where the hydraulic head is no longer sufficient to lift injection zone brines to fresh water. That is how EPA defines area of review. Within that boundary, we worry about hypothetical open wellbores. So what EPA says is that every injection project has to identify an area of review based on predicted pressure elevation of the project. Within that area of review, you are required to review and potentially remediate all legacy wells. Right? Make them secure, because these things are fast paths through the geologic seals. Which is why things like Spindletop are terrible ideas for storage. Full of hundreds of old 1900s wells, no thank you. That's a hell of a lot of risk and cost to remediate, if you can even find the wells. Gulf of Mexico, as it happens, has 1.1 million legacy penetrations. It has been a prolific hydrocarbon basin. We know a lot about it. We sampled it 1.1 million times. But that's 1.1 million holes in the geologic seals. Our quest for running room is to avoid the highs where all the wells concentrate and go down dip. So this is a map of southern Louisiana, southeast Texas. The structural closures are shown by the blue outlines. Black dots are wells, and you can see where they cluster. Occasionally there are little bits of salt that poke through this. That's the pink stuff. faults are in the dark lines. And our quest for storage is to go down dip, to look at those well-free areas, and to try to keep the pressure footprint of injection projects from touching the wells. That's how we keep this economic. So take an example. I've got a prospect here, more or less encircled by faults. Maybe you could call it closed boundaries. It's about 400 square kilometers, and you'll notice there are some pretty good-sized areas down dip that are completely free of wells. What if we put an injection project in it? So if we give it typical Gulf of Mexico properties, 25% porosity, 100 millidarcy perm, 400 square kilometers, which is what we measure inside that circle, inject 1.5 million tons a year for 20 years, 2.5 kilometers depth, 100 meters of reservoir. The graph there, bottom one shows you the CO2 plume. It doesn't go far. Top one shows you pressure. And pressure, as it happens, our threshold pressure in this case, the limit for defining the AOR, is about 1 megapascal. And in this case, our minimum pressure buildup is about 4 megapascals. We've pressured up the entire compartment. Every well in there is within our area of review. All right, back to the drawing board. Let's add more reservoirs. Bigger volume, bigger tank, less pressure, right? We can do this. We've got lots and lots of sands here. We can add more of them. And if you put in 400 meters of reservoir instead of 100, you can keep the area of review nice and small. That's the dashed white line. So that little circle around the injection well. Looks good, right? But you saw there are a lot of projects here. If another guy comes along, puts his own project somewhere else in the same compartment, identical to yours, between the two of you, you again pressure up the entire compartment. It is all back within area of review. In essence, what we do is take this model, one isolated project, pressure grades off with distance, we add a second well to it. And even though they define their own areas of review, that little fringe pressure beyond the area of review is enough to add together and elevate that stuff in between, the land in between the projects, over the threshold pressure. It all becomes statutorily reviewable. Whose pressure is it? Who has to review it? I don't know. Right? This is untested stuff. But what you realize is that accurate forecasting of impacts and pressures and remediation requires considering all of the projects that are in pressure communication, not just one. So the view that this brings us to is that pore space is only part of this. The key commodity is pressure space. Right? Pressure, headroom, times pore volume. Right? Just like a gas storage tank. The regulations focus on pore space. They require you to lease the acreage to be occupied by CO2. But the business of injection requires pressure space. And if you don't guard the pressure space, which of course is a much larger area, you may be in trouble. So what do we conclude from this? You know, I've given the storage volume a serious haircut, right? 125 gigatons down to 10 gigatons. It sounds disastrous. It isn't. 10 gigatons is a lot of storage, right? And this is one little slice of the Texas coast. We could fill this, we could move along strike into Louisiana, we can add other reservoirs, we can go offshore, we can go up dip. There's a lot of storage here. Storage capacity is not going to be a limitation. But, and the current developments are exciting. They will be very impactful, right? This is not to say that they won't work. But as we've seen, CCS is not petroleum, right? We need to change how we think about storage. It's not just pore volume and some saturation figure. It's pressure, pressure space. That pressure buildup limits injectivity, it increases the area of review, and it means you have to consider all of the projects, not just your own. Pressure space is the commodity. The implications are things we're just starting to work through. But of course, if it's pressure space and you need more acreage, it impacts project spacing. It impacts what you lease for a project. It impacts the regulatory view of project spacing and project monitoring and operational design. There's an implication for land value, and of course an implication for monitoring. So stay tuned. It is a paradigm shift in how we think about storage, and of course, like all paradigm shifts, it takes some time to work through. I've been talking a lot with California regulators about how this works. Texas is not far behind. So let me say thank you to Department of Energy, who sponsors much of our research, our industrial sponsors, who take care of the rest, and of course the Gulf Coast Carbon Center, who is invaluable in shaping the ideas and discussing with me. And thank you, of course, for attention.